Okay, we'll get started here in 2 or 3 minutes. Okay, let's get started here. Um, I think, the group chat available, which is an option over on the left-hand side, the top icon. And if you guys need to ask any questions, we can do it through that. let's see here. Or otherwise, just shoot me an email if that doesn't work for you guys. Okay. I'm going to set up some backup recording in case the quality of this doesn't turn out too well.
Hi, this Getting Started project will...
Okay, got that started, so let's start up. For any of those watching and able to get to the group chat, just send me some kind of message through that to let me know if you can hear and see everything properly. That way I know everything's working good on your guys' end. Okay, well, I'm just going to plow forward and start covering the material. And what you should be able to see here in a moment is my desktop shared out to you guys. If the quality of this ends up not being very good through Google Google Hangouts or on YouTube, I am using desktop recording software right now to get a very high quality version of this just in case as a backup option. Okay, so where we left off last time around, let's see here, was with the different types of operating systems out there. The last few that I wanted to cover fairly quickly here were real-time operating systems, all the way up through monolithic kernel operating systems. Let me get this zoomed up for you guys. So the goal with a real-time operating system, and these are still very much mainstream systems that people work with to this day. These are used when the most important concern is completing a task on a deadline or at regular intervals rather than the actual performance. So on some level here, latency is the chief concern compared to throughput. But it's really about primarily about meeting a deadline. So an example might be a measurement system, a scanner, medical applications, industrial applications, things in automobiles like anti-lock braking systems, traction control, and things of that nature, where sensor input needs to be taken at reliable intervals, actions need to be taken at reliable intervals, and there is a deadline upon which the computation needs to be completed. These systems often use some form of cooperative multitasking. That and how they achieve this scheduling, I will go into in a subsequent lecture when we get actually into the problem area of process scheduling. The common examples out there these days are QNX, Micro-C, VxWorks, and some layered systems that are typically in-house built on top of MS-DOS. VxWorks is famous for being on things like the Mars rover. I don't know about the current one, but I know one that was out there in the years past, not too long ago, was using VxWorks. QNX is not an uncommon system in automotive applications and in other industrial concerns. So definitely an important thing to be aware of. And we will definitely dive into this as the class progresses this semester. The other two big, let's see here, I just got a message. Awesome, people can hear me. I'm using my cell phone to read the messages. Okay, there, in the late 80s and 90s, and even into the 2000s, there was a lot of debate over the architecture for an operating system. There were questions of complexity, of reliability, and of performance. And the two common approaches were known as the monolithic kernel and the microkernel. The microkernel, it is a very basic, very minimal operating system kernel. It will include things like virtual memory management, if even that, some driver management, some very limited driver management, some process scheduling, and system call handlers will be in this very simple microkernel. The higher level operating system services such as the swapper, most of the drivers, process scheduling, and most of the system call handlers will be actually in separate processes in the operating system. And the theory behind this is that you have separate components, which are hopefully resilient to failure. If, for instance, a driver were to crash, the idea would be that it would not take down the OS, you would not get the blue screen of death, as you historically would in Windows, and that the microkernel would be able to restart these. The microkernel is typically a very small piece of code. The downsides to these approaches is there's a lot more context switch overhead. So the price that is paid to make a call from an application into the operating system for some service, or intercommunication between the operating system services. There's a lot of overhead spent here. And an area of complexity that you pay for is that there are a lot of message passing schemes between the operating system's services. And as we get further down in the course, some of these can turn into distributed deadlock problems and can lead to fairly complicated code. And just having to deal with a lot of extra concerns. So some successful examples of microkernel OSs, one would be Minix, which the author of our course textbook is famous for having built. OS X, which is built upon the microkernel, unless they've changed it recently, of Mach. So yeah, OS X is actually a microkernel OS. Another one out there, it's not heavily used out there, but it is out there, is called Herd. And part of the reason that I bring it up is that they use the L4 microkernel, which is another common microkernel that a lot of projects out there, make use of. Monolithic kernel OSs is the idea that the entire core of the operating system is inside of one program and one process. So examples would be earlier version of Windows, earlier versions of, or actually most versions of Unix, so AX, HPUX, Linux is a monolithic kernel, and the BSD operating systems also are. Interestingly, for those who have followed macOS, some of the code in macOS comes from FreeBSD, but the core of the operating system itself is a microkernel. So it's sort of going a little bit of both ways. These typically perform better, and many people believe that they're easier to develop for. If you look at the purported advantages of microkernel OSs, a lot of claims were made about Minix that it could survive a lot of driver crashes, it could handle major components of the operating system going down and could recover them. But the reality has been that when I've used it, it's definitely very possible to have that OS completely crash on you. As far as the Apple operating system, OS X, you know, very different. So there's something to be said for having a lot of money and having a lot of talented developers too. So a lot of the concerns over reliability, for example, in Linux, you can build a device driver that can have a large category of different types of faults and crashes, and it really will not crash the operating system. So some of the criticisms and differences between these two approaches have had interesting, unique solutions. These days, Windows, so ever since probably Windows XP, and it became especially true when Vista came out, and it's very, very true these days. Windows is sort of between a monolithic kernel and a microkernel. They have greatly limited what runs in the OS kernel, and they have pulled out quite a bit into separate applications. Distributed OSs are interesting to study. For the most part, these are sort of a failed branch of operating systems. The author of our book wrote one called Amoeba. The original developers of Unix built one called Plan 9. And if you ever get a chance to play around with a distributed operating system, I suggest giving Plan 9 a look. They have a lot of really unique, very interesting approaches to distributed computation. There was also some attempt, to some extent, to make this a possibility in Linux. Didn't gain a lot of traction. When we talk about commercially successful examples, I couldn't give you an example of one. Most of these distributed computing is really accomplished by languages and frameworks that are outside of the operating system and through third-party software. And it's really been not relegated to the OS, but relegated to other application software. So let's move on to processes. So let's see here. This site is not cooperating. Rezoom this guy. That's unfortunate. We will do this. Okay. Okay, so a process is really the fundamental building block in an operating system. Just to give a good high-level overview, let me switch this screen share off. Okay. Just to give a good high-level overview of really the goal of a process. So early operating systems started out with a single application that was using the resources of the computer. Time-sharing systems came around and allowed the computer to stay continuously busy, allowed different processes to use the hardware in parallel to create better utilization of the computer system. The goal of the operating system is really to create a view of the world to the process that is very simplified, does not have any of the hardware concerns or specific low-level details exposed to the application. And another important part is that it is there to provide a safe sandbox for the application, meaning that the application can view itself as the only application running on the system. So if you've got a word processor and a video playing on your computer, those two processes don't even need to be aware that the other one is running. They can each treat the computer as if they have it entirely to themselves. That kind of separation, that kind of creating a simplified model of a computer to the application is very important, role that operating systems fulfill. Okay, let's see here. Sort of the screen share again. Okay. Hopefully that's showing up. Yes. Here's what it is. Okay, good. So, what is a process? It's an executing program or job, so it's an instance of a program. You can have a program loaded more than once. So if you launch a word processor twice, you have two processes executing one program. The process has a set of very important components. The memory address space, so this is the view from the program of the memory of the computer. When we get into virtual memory in a little bit more detail, we'll see that the OS does a lot of work to give the process a linear address space that it can manage, and does a lot of work to allow programs to have a memory address space that can even be bigger than the RAM installed on the computer. Another important component is the program image. So this is, the program binaries themselves. Handles to files, so, and this can be expanded to other operating system capabilities, so it can be handles to screens, to sockets for networking, to microphones, to webcams, and other things. So a process has associated with it a set of resources that the operating system is managing, and these handles are used when making calls to the OS to say, modify this file or read this amount of audio from the microphone. Processes also have inter-process communication, or the ability for two processes to communicate with each other. We're going to have an entire lecture about inter-process communication. In both Windows and in Linux, every process has a parent or a creator process. In Unix, the topmost process is called init. When a Linux operating system boots, the first program to start is called init, and that in turn launches the desktop, the console, the system services, and whatever else is out there that needs to be started. In Windows, there are a couple topmost processes. As of Windows 7, this may be a little bit out of date for 8, but I don't think it's changed. System.exe is the OS kernel. CSRSS.exe handles the interface between the OS and the applications in the OS kernel. WinInit manages system services, so background processes that do things like managing. Let's see. That's a good example. Things that like index your file system or provide search capabilities or manage network connectivity, provide updates for your system, things that run in the background that are non-interactive. Explorer.exe is the OS shell, so it is what basically regulates the desktop. WinLogin.exe is just the OS login service, and it, to a great degree, manages permissions on the system. Okay. Let's see here. And the next bit that we'll talk about is the process memory layout. So when a process starts, it has to get loaded into memory. Different parts of the process need to be loaded into memory. They need to have a certain layout in memory before the execution of that process can begin. The part of the OS that's responsible for this is known as the loader. This can be something that partially runs inside of the OS and partially outside, but typically it's also entirely in the OS. And there are different components of these processes. So these are the ones to look at. Text is the machine instructions of a program, so that actual executable in its library is loaded into memory. Data is initialized static data and constants. BSS, which I've always found is an interesting acronym, is the uninitialized static data. And we're going to look over a code sample here to delineate what these two are. Heap is the dynamic memory of a process. So you can have one or more of these per process, and it's basically the area where when you allocate new data structures, you create a linked list or a binary search tree, you're going to use that heap to dynamically create and then dispose of in-memory objects. The stack, which those of you who've taken data structures will remember, is itself a data structure. But the stack is what the area of the process memory layout that contains local variables, the call stack, return values, and there is one per thread of execution. And we'll get into the distinction between kernel mode and user mode threads later. But basically, you get one of these stacks per kernel mode thread. So yeah, here is a picture of the memory layout of a program. So let me switch the screen share over here. To be the full desktop. Okay, and we're going to look at an example inside of Linux here. Okay. So, let's zoom in on this. me increase the font size. Okay, here we go, font size. Let's do 16. Okay, that should be good and visible. So what we have here, and these are in the system code samples. If you look on the Piazza site here, and you click up on resources, let's see here. Yep, all the code samples that you are going to see in the lecture for the rest of the semester are publicly available at this URL. You can download a copy of this repository, and you can go through these on your own at home. Okay. So I'm gonna build the case all built, and let's see here what we got here. Okay. So here we have a fairly simple program. It runs a series of tests for an application that's built here, and it's basically testing various data structures. In this case, it's testing add, remove, and get operations on a list data structure. So in here you can see examples of variables that are allocated on the heap. In C++, when you see the new keyword, that's something that's allocated in the heap. A primitive type value here that's local to the function. This is allocated on the stack, and it comes and goes with the function call. Again, return values are also handled on the call stack. And here we can see an example of a value being deleted from the heap. Let's take a look at the list. So I don't think I have any examples here of BSS data, but I'll create one here. In C++, an example of BSS might be this. I've created a global variable. It does not have any value initialized to it, so it'll be in the BSS section. If I have a constant defined, this will go into the data section. So the difference here is whether the variable is initialized at compile time or it is not. Excuse me for a second. Oh. Sorry for blowing my nose over the internet. Okay. So I wrote a little script here called layout, and what this does is this uses the size command, and what the size command does is it looks at the, in Linux, it looks at the memory layout of a process. What things are going to get loaded into memory, where they will be loaded in on default, and the relative size of these. So I've written a script around this program to print out the parts in this process. And what this will tell me is that the text of the program is of size 3,666 bytes. By default, it will be loaded to this memory address. The data for the program is just 16 bytes and will by default be located here. BSS will be located adjacent to it. As you can see, these numbers are 16 apart, and will consume 8 bytes of memory. Okay. So let's see here. Switch to a single app so that that looks better. Okay. So when this gets laid out in memory, this is a typical way that it may look. You're going to have the call stack and the process heap. And these two are going to grow towards each other. As you need to allocate more and more data structures, the boundary of the heap will continue to grow and grow and grow until there's really no more space for it. As you make method calls, you have local variables, you have a certain depth in your call stack. That will continue to grow down. And these two essentially grow towards each other. And in reality, this unused region is actually quite large. It's not quite as small as this diagram displays. So it is really up to individual programming languages like C#, Java, C++, Python, to really control how these heap and stack sections are managed. The BSS and data segments typically are located near the heap, and that just helps data locality. And then the text segment is located at the basically the end of the process address space, and this contains the instructions that are executed by the CPU. A capability that most modern operating systems have is that within one process, you can have multiple threads of execution. So you can have one thread of execution in a process downloading a web page, a second one playing a video, a third one playing the audio, a fourth one rendering some text or an animated image on the screen. You have lots and lots of threads launched. Let me switch over to the desktop view here. Okay, and I'll show you an example here on Windows. So if we look at the task manager here in Windows, we can get some information about the threads. Oops. And we can see here if we, let's say we run Notepad. Yep, all over there. Okay. Let's find Notepad in here. So here, this has one thread of execution. Basically interacting with the user, accepting the text that's typed in, handling save operations, and things like that. However, if we launch a more complicated program like Internet Explorer, we can look at Internet Explorer and see that for some reason they launched more than one process, but there are in the main process, there are 20 threads of execution. So those are 20 different places in the code that are potentially executing simultaneously. Set this guy. Okay. When you have these multiple threads of execution, they each get their own stack space. So you can have two method calls running in parallel, and they each have their own call stack. I'm going to do an example of that here in Visual Studio for you guys. Switch this back over to desktop mode. Let's close this down and fire up Visual Studio. And the example that I'll be doing for this will be in C#. Okay, and what we're going to have here are two threads of execution. And what this function will do is it will call with some silly program. And let's define that function. And we'll just put that out to the console. Another function is just going to do math problems. And occasionally print things. So okay, so fairly simple program. And what we're going to do is we're going to trap this in the debugger. So we'll launch our two threads first. And in .NET, one of the ways to launch a thread is to use a thread object. And what we do is we pass in a method here. So print x. So let's call this guy thread1 and thread2. And we can start these two threads. And that's to make sure that the main process doesn't exit on us. So let's see here. What we'll do is we'll start execution of this. And you can see it's printing like mad. And we're going to pause the execution. We're going to see what's going on here. If you look in Windows, what you can see here are, let's see here, threads. into the key screen. So what I'm going to do is pull that down here. And what you should be able to see here is all of the threads that this application is running. So if we look at the console application, we've got 13 threads. Not all of them are visible to .NET, but most of these are. Some of them come from the actual framework. And what we can see here is the location in the code that they're both executing. We have the main thread, which is waiting for input on the console. We have 2 different threads of execution printing values. And what I want you to notice over here is we have 2 distinct call stacks here. This is the print addition function from one thread, and if we go over to this other thread, we have this other function executing at the same time, which is the printx function. And you can see that both of these have independent call stacks. And let's go back to processes. Okay. So I have a link here. I'm going to make sure this link works. It doesn't. I'll update it to the correct link. We moved everything from Google Code to Bitbucket, so I need to fix that link. But once that's fixed in the lecture notes, you'll be able to look at the layout example that I did in Linux. So we're going to pick up the pace here, and we're going to talk about how programs are actually loaded into memory. And then we're going to get into an example of how they interact with the actual operating system. The process for loading a program first is for the loader to make a call to the operating system to allocate memory. And it'll basically allocate memory for the text, data, BSS, the heap, and the stack. And then it loads the program's image into memory, so the actual executable. The loader gets information from the OS where shared libraries are located, which ones are already loaded into memory, so it doesn't have to do this work again. And shared libraries contain their own text, data, and BSS. One way that you can see this is with the nm command in Linux, which we'll do right now. So, nm demo. Actually, okay, I want to show this first. So this is our little demo application. And these are the shared libraries that it depends upon. This one right here is the library that provides the C++ runtime, so handles a little bit of the memory allocation, handles being able to write to the console, and is a lot of, when you have include statements in a C++ program, the common library resides here. The C common library is here, is libc. So the part that's not specifically C++ is here in libc. So functions like printf, let's see, what else would be in there? Basically terminal I/O, calls for file I/O, and a lot of the ways that C and C++ can call into the operating system. libm is a mathematics library, so it contains functions do, sine, cosine, tangent, and several others. So let's look at the actual, make sure I've got this right. Oop, I'm not sharing full desktop. Oops. I think I'm just going to stick with this. Okay, good. What you could not see when I wasn't sharing it earlier, when you run the command line program LDD against an executable here, we have our demo program. It shows the libraries that this program depends upon and where they're located in the file system. Let's see, what else does it show? Quick look, and yeah, okay. So another program that we can run is NM. And what this will do, at least for C and C++ programs, is it will print out the symbol table for a process. So you can see here are basically a lot of compiler-generated functions. Where all these functions are actually located in memory when the loader loads them. And you can see here is our main function. Okay, it's located at the hex address 401.18b. But you see other functions right here that, well, they don't have an address. So printf, that's a function from the C library that prints to the console. So why isn't there any address? Well, that function is actually implemented in the standard C library, and it's not duplicated into this program. When this program is loaded into memory, the OS will also have to load that shared library and put an entry into the program to tell it where the address of that function is so that calls can be made to it. So anytime that you see this U thing right here, that's what that is. This right here, this funny naming, is C++ convention where they have class name and function name. And then they have different characters to denote different parts of the signature. Yeah. So when the loader loads, it will load the main program, and it'll load these shared libraries, and it will fill out a table in the program telling it where all these functions are located in memory so that the program can properly call them. Internally, there are a few compiler-generated methods. The program has a start method, which sets up some stuff for getting the program running, so it gets the console ready, and a few other things like that. Each library has an init function, which will basically go through and initialize static or global variables and set up things on a language level. And then after that, the start function will call your main, and your program will go off executing. So there's a bit of a complication here for loading shared libraries. So when we look at what this program demo was making use of, we've got all of these extra libraries here, and those have to get loaded into memory. Now, the OS does a neat little trick for you. Tons and tons and tons of programs on the system are going to require the C standard library. Lots of applications require this. It would be a little bit inefficient for the operating system to load this more than once. So if you launched 1,000 applications, you really wouldn't want 1,000 copies of this library in memory. It would be a waste of memory. It would be very redundant. So the operating system does a little bit of extra work to make sure these libraries are only loaded one time. Now, the difficult thing there is here we have to go into a concept that we're going to explore at the later lecture called virtual memory. And basically, when you look at the addresses in this process's memory layout, they are addresses local to this program. So in every program, there might be an address 1000. Another program can launch, it has an address 1000. If they both write to that same address, they won't be writing to the same spot in RAM. The OS will give each process its own, the term is virtual address space. And this is different from physical RAM. When these shared libraries are loaded just once, so that they only exist in RAM once, they're loaded in physical RAM, but when they get mapped into the individual process, they may not exist in the same space of the process. So if we look here, and let's look at just these two libraries. If libc were loaded at address 1000 for program A, and then libm were loaded at address 2000 for program B, that would work out. Program A would be fine. So both those are loaded at address 1000 and 2000 for program A. We have another program, program B. It decides to load libc at address 1000, so those are the same. And then it decides, well, I'm going to load the C++ standard library or some multimedia library at address 2000. And then it's going to load libm at address 3000. Well, if we look back to where the functions, the symbol table here was set up, these are all set up at specific memory addresses. And if you look inside the libraries with the same command, you'll see that they each have you know, some concept of addresses there. The trouble is that when a shared library is mapped into the address space of a running program, you don't have a guarantee about where in memory it's going to get loaded. But when you make a function call with a CPU instruction, you know, when we're looking at, let's see here, the main method, when we call printf to print to the console, that printf function exists at a certain place in memory. And the call, or the jump instruction that's used to work with it, takes an address. And these libraries may internally print to an address, or make a function call to that same address to print themselves. The trouble here comes in these different libraries getting loaded in different virtual addresses in the process's memory space. So how in the world is this handled? So actually, yeah, okay. So the way that this is handled, actually I want to draw a diagram here. Let me see if I can get Google Hangouts to let me do that. Okay, let's see. Nope, that's not what I wanted. Let's see if I don't have a drawing tool here. Oh, here we go. Let's screen share and I'll just use Paint to do this. So the way that this works out is we have two processes in memory. And down here will be the actual program for each of these. And let's see here. This will be program A, and this will be program B. When they load their reusable libraries, something like might get loaded here in one process, and then in another process, let's see here, let me think of an example. So you could have libssl. So libssl is a library that lets you create secure network connections. And these two are in the same spot, but when this other process loads its C library, it'll be at a different address. So when both of these guys need to call print function in libc, they're not going to be at the actual same address. So how is this handled? The way that this is handled is there's a special capability in the compiler. So what the compiler supports is the concept of position-independent code. So libraries have a data, BSS, and text segment, and memory positions within the library are position independent. They're basically all calculated as offsets from position in memory. So all of the addresses that are in libc are calculated as offsets from the beginning of libc. And the same would be true of the SSL library here. They're all calculated as offsets. So internally they're consistent, but when we look at how these libraries, so if libssl needed to call something in libc, or B needed to call something in these functions, we need to still be able to wire all of these up. You know, here we still need to fill out this guy right here. We need to know where all these functions are. And what this is termed is the global offset table. When the program is loaded, there's a special area in memory called the global offset table where all of the function addresses are filled in. Basically that gives the program a directory to look up the addresses for all of these functions. For the C compiler, FPIC is the position independent option. So there's a lot of hardware support for this. That it sounds like a lot of extra work, but the hardware is built to handle this. So let's look at it. Well, let's look at an actual example. Here we have a simple program that we are actually the demo program that we showed earlier. And here we have our local variable from a function call. We're printing and returning 0. If we look, we can ask the C compiler to show us the actual CPU instructions that we use. So if we just compile that program, we can see all of the CPU instructions that are put out. You can see the main function here. You can see the function call to run test. You can see the function call to printf. And you can see the return in the program. Now, if this is compiled with position-independent code, so let's see here. There is a small difference. I believe it's so that small difference is right here. So this is the example where a special register here is used. So you don't see that CPU register over here used at all, but this RDI and RAP register are used for that global offset table. This is basically how shared libraries are able to wire in together. We'll do another example of this and explain a few more cases of this when we have lecture next week. Another thing to bring up is shared libraries versus static libraries. When you're building a program in Visual Studio like this, you have this program. I can create additional libraries that go into this program. So I can create a new class library. This main program will consume. And this is an example of a shared library here, where I can create whatever reusable functionality I would need. The difference out there, so most of these libraries are shared, but there is such a thing known as static libraries. So the advantage for shared libraries is it reduces the memory footprint. If two programs load the same shared library, a large chunk of that memory is reused. You don't use extra memory. And this is thanks to the use of the global offset table. The disadvantages is it requires a bit more of an advanced operating system and advanced compiler to be able to do this. When we were looking through how these shared libraries are loaded and the difference between regular code and position-independent code, these are all things that have to be implemented in an operating system, and they are, they have a certain amount of complexity to them. So fairly simple operating systems usually don't have shared libraries. They'll rely on static libraries quite a bit more. Static libraries have an upside. When you don't desire reuse, you want that faster first load, so you're not setting up a global offset table, and fewer instructions are generated. So this is a bit of a trade-off that when you guys start developing more complicated software that you'll have to think about. Whether you are using shared libraries or static libraries. With the approach using shared libraries through dynamic linking, your program will have a smaller memory footprint. You'll be able to have code reuse. You'll be able to upgrade those libraries independent of the program, and your actual process file size will be smaller. With static linking, you don't have to worry as much about library dependencies. When we did that LDD call right here, Yeah, okay. All of these, if you're doing static linking, all of these libraries would be duplicated into that demo process, so you wouldn't have those external dependencies. Um, and you get some advantages in terms of trying to obfuscate your code so that you can protect it against people decompiling it and seeing your trade secrets. And there are certain compiler optimizations that can work across modules in a program. So that sort of concludes the part about process memory layout. So that really covers this part of, well, about half of this part. We're going to cover the other half of this part next, and then hopefully we will get into a little bit of communication to the OS in this lecture. I think we'll end up rounding up the rest of this introduction into processes probably next Monday, but we'll see what we can get through here. So another important thing that operating systems offer to processes is the concept of process protection. So the following protections to a processor are afforded by modern OSs. One process cannot read the memory of another process unless you do explicit work to permit it. So your web browser can't read the memory of your word processor or out of your calendar unless you give explicit permission. So the data in these separate processes can be considered secure. Things won't get messed up. A process can fully manage its own memory if it so chooses. If your program crashes, has an exception, resource starvation, deadlock, any other kind of way that a process can crash will not crash other processes. And another big advantage here is that when the program is mapped into memory and the part of the memory is managed by the kernel, the OS can't accidentally modify parts of the OS. So an example would be in the days of Windows 3.1 or Windows 95 or 98, what could happen there is if your program misbehaved, it could overwrite part of the memory of the Windows operating system and very, very quickly take the whole computer down. Modern operating systems do have protection here. Let me see if I want to do this. Okay. Yeah, actually, I think we're going to get further than I thought. Okay. So how are processes created? This is something that differs between Linux and Windows a fair amount. In Linux, they have a system call called fork. And the idea with fork is fork duplicates the running process. So if you have a program, performing a certain operation that calls fork, it will duplicate that process in memory. When the fork call returns, it gives different return values back to the call. If you are the child process, you get a 0 back. If you're the parent process, you get the process ID of the child. So here's an example of this kind of behavior. Here in our main function, we call fork. So the effect of this is we're going to have two processes. We're going to open up a file on the file system, and we got a message from the parent and a message from the child. And what we're going to do here is we're going to write to this file and print something out to the console. And if it's the child process, we're going to do some different behavior here. And if creating processes fail, we have this other case right here. So let's do this example here in Linux. We're going to build this with make. And let's look over. So this is the same code here in the lecture notes. Oops. Except I pressed the wrong key and added a bunch of new ones. Okay. Clear the screen. And let's look at the output file here. And we can see some interesting behavior here. Here we can see the two processes printing to the console. After fork, there are actually two processes here. And we can see the parent and the child both doing something. If you look back at the code here, the idea, so you can see here the parent printing and the child printing to the console. What the parent is going to do is write several twos to the file. Or, sorry, the parent is going to write several ones to the file. The child is going to write several twos. Now, what we have set up here is a call to sleep, and what this will have the effect of doing is having the parent pause to give us some level of guarantee that the child will execute first. So what will happen is the child will write all of these values to the file, and then the parent will write all these values to the file. But we get a bit of an interesting effect here. If we look at the output of this file, well, we basically wrote all of these twos out, and then the parent overwrote part of it with all of these ones. Okay. So really, in terms of what the child wrote, it should wrote all of that. But when the parent wrote into the file, it overwrote here. So why did that happen? Well, when the process is duplicated, here we do an open call. You actually get the file open twice in both of these processes. So they have their own separate file handles, which is what this is right here. This is a handle to that open file. And the open call asks the operating system to open it for us, and the close asks the OS to close that for us. And what you can see is that the position that both of these are writing to the file is actually independent. So when fork is executed, everything is duplicated, and everything gets its own copy, including separate file handles and things like that. So this is what happens with process creation. If, like in our other example here in Visual Studio, that we were creating two separate threads instead of two separate processes, with threads, objects in memory are shared. With processes, they are not. And that concept comes from the idea of process protection. So one process cannot read the memory of another process. And if we recall the memory layout of when you have two threads, all you do is have two threads of execution, but they do share everything else. And that's really the real distinction between processes and threads, is that level of protection and the degree to which they share objects in memory. So this is a little bit lower level. There is another system called Linux called Clone, and Clone can allow for finer-grained sharing. So the fork system call will duplicate file handles, file system information. It'll duplicate all the memory for you. But you can do a finer grained job here and only duplicate a certain amount of things between two processes and share other parts. So this is what really creates the difference between a separate process and a thread, is the different ways this memory is allocated. Okay, let's look at Windows. Windows has two function calls out there called create process and create thread. It's very different from the way that it's done in Linux. Create process basically creates a brand new process. Roughly it's the equivalent of fork. Create thread creates a new thread. Roughly it's the equivalent of clone. The difference is create process does not do any duplication of the process. It is really just starting another program. Is this a disadvantage? Really no. Is it a real advantage? No. It's just a different approach. And if you want to, there are libraries out there that do a little bit of a complicated job of implementing a fork-like call in Windows. Next little bit here. What causes a process to end? When I've got a process launched here, I've got Notepad. What happens when I close Notepad? What does the OS do? How can that happen? So what causes a process to exit? Well, one case is that the program finishes. It has a normal exit. Another way that it can terminate is to have an error when it exits and indicates some kind of failure. And then there are several different ways in which a process can crash. A seg fault or bus error is an example of where a process tries to read or write in an inaccessible area of memory or write to read-only memory. A stack overflow is where the stack pointer grows larger than the stack area. The example of that would be up here if the call stack kept growing and growing and growing and actually overwrote other sections of the program. And usually that kind of thing can happen when you get into an infinite recursion. Protection fault, there are certain CPU instructions that only the operating system can execute. If your program tries to execute those, you get a protection fault, your process will be killed off by the OS. There are other things like divide by zero or other instruction faults that can also terminate a program. And the other way that processes can exit is through external termination by another process. So an example of this in Windows would be if I have Notepad running and I go over here to the Task Manager application and I say, okay, end. That is one program closing another. So that's the other way. I'm going to skip over this. And then we've really covered the basic for processes, and I'm going to do a little bit into how some of these system calls work in the operating system, and this is going to be the basis of our first homework, which I'll wait to assign to the next lecture so I can talk about it in more greater detail in the class, and you guys can ask questions directly. So, where am I? Okay. So, we've covered how the operating system loads processes, how these processes are laid out in memory, how they're protected, how process creation happens. But in general, we need to be able to do some useful work. How do we communicate with the OS? How do we read and write files or open up network connections or things like that? It's through the system call. And a large category of system calls into an operating system are file-related. So let's go over that specific file-related case. So let's start right here. The types of files that are in Unix. Regular files, symbolic links, so this is a pointer to another file. So an example of a symbolic link would be here. If we look at the libraries, if we look at this library right here, this is a symbolic link. Let's look at it in a little bit more detail. Oops. So here we have the real library file, and then we have this symbolic link. And basically this is a file that points to another file. That's all that is. Folders, of course. And then we have two file types here that model devices, block devices and character devices. So I'll show an example of these. In Linux, if you go to the /dev folder, you see a lot of interesting things here. These are all of the real and virtual devices on your computer. So here are some files related to your CPU, to the disk on your computer. Let's look under disk. So here we have actually files that represent the CD-ROM drive. And let's go to input. So here we have the mouse, which is a file on the file system. Okay. And in Linux, the way that we can interact with these devices on the computer is actually through making function calls such as reading or writing to and from these device files. Yeah, so that's sort of the way, on a very, very high level, that Linux, as an operating system, abstracts the hardware to a process. Another area are inter-process communication, so the way two processes communicate with each other. These can be represented on the file system, and we'll talk about these a lot more when we get into inter-process communication. Oops, there we go. So regular files, those are just files on the file system. I think pretty much everybody knows what folders are. And I explained these. Okay, let's skip up here to file system calls. So majority of the system calls, as I mentioned earlier, in Unix are to work with files and folders. MS-DOS is an early Microsoft operating system, and it stood for Microsoft Disk Operating System. And really, the DOS part of that acronym seems to really greatly apply to almost all operating systems. If you look at the system call lists that's out there, the file system calls, they're about 70% of the ability of what Linux has to offer. Amongst these are open, which can open or create a file, create, can create a new file. Interesting thing here is how it's spelled. It's spelled C-R-E-A-T. You might ask yourself, well, where's the E? Because create comes with an E on the end. Well, there was some irrational fear of wasting a byte. So, for some reason, they decided to not have the E. It was a decision made in the 1980s, actually late 1970s, and who knows why. Close will close a file descriptor. Lseek will change the position you're in within a file. Read and write are pretty self-explanatory. They both read and write from a file. Dupe and dupe2 are interesting. Dupe will duplicate a file descriptor, and dupe2 updates the file descriptor. And these system calls are basically how you do something like this. If I say echo hello, that command will print to the terminal hello. If I do echo hello, it will write it to a file. Well, how did that happen? The way that this is implemented right here, the way I redirected that out to a file, the way this happened right here is through, in this case, the dupe2 system call. That it basically updated the file descriptor for this console, and instead of writing to this console like it did here, dupe2 was called to say, well, instead of writing there, write to this file. That's basically what that does. File control function will do some advanced properties of files, setting things like asynchronous I/O, file locks. I/O control is sort of a catch-all interface for interacting primarily with device files, like that mouse device file that we saw, and working with some atypical properties that are really specific often to a particular device. Stat returns and allows you to set, actually stat just gets the statistics for a file, so the size of the file, when it was last modified, what the permissions are. Access basically tests whether or not you have permissions to read a file. Let's see here. Looks like people are mentioning that the video stopped, so let me restart.